Thank you so much for staying late on a beautiful Friday afternoon. I hope I'll be just as exciting as the sun. Probably not, but at least if you're from Boston. If you're from California, then you're stuck here. Okay, so thank you so much. So our company is called Gamelon. And we've been really a research lab for a long time. So we started actually in 2013. We were really the largest investment from the federal government in trying to move from deep learning to next generation and machine learning. So I'd like to show you some pretty cool new stuff that we've never shown anyone before. And we're using this for a wide range of customers because we are a business, and that includes some really big tech firms, health insurance companies, automakers, companies who make like robots and factory automation, and banks, financial services companies. We've been covered before, but I've never shown anybody what we're going to show you today, and I'm really excited about that. My background, I'll kind of skip over this because it feels sort of egotistical. But I started doing deep learning when I was a kid, actually. I was part of a science fair project, and then ended up in David Rumelhart's lab at Stanford when I was in middle school, and was adding momentum terms to backpropagation. I just kind of fell in love with machine learning, and I decided I wanted to devote my life to trying to do the next big thing. So hopefully, that's this. It's been a long, I guess that's been 30 years of to this day, to this moment. So if it really sucks, then just at the end, don't tell me, because my whole life will be for no reason. So we've got a general platform, a new approach to machine learning, and we're applying it to a bunch of different kinds of data science challenges, but where we're really focused right now is on natural language, because it's kind of an open frontier. We've got pretty good image processing. We can recognize faces. We're doing pretty well in a variety of areas, but natural language is hard. And so that's where we've decided to kind of show off this new technology. Since we're all data scientists, can I do a little bit of data science? So I was just curious if you could raise your hand if you are a technologist. And then could you raise your hand if you're more on the business side of working? Okay, great. And could you raise your hand if you're from like a startup company or a company smaller than 20 million in revenue or something like that? Okay, little companies. And then can you raise your hand if you're from a big company? Interesting. Okay, so that's a little bit of data. We'll collect a little more data at the end. What that tells me is I should show you guys some business stuff and some technical stuff. So I'm going to do both and try to satisfy both audiences. Yawn loudly if you are in one camp or the other and you're not getting enough of what you need. So the trouble with natural language is that one sentence can express over 10 billion different ideas. Right? Actually, probably more than that. I was trying to be conservative. And so it's hard to classify sentences, for example. Like the normal things we do with machine learning, like regression and classification, like let's put sentences into buckets. Like how many buckets could you have? 100 buckets? 1,000 buckets? You're not going to have 10 billion buckets. So we're missing something, right? We're missing some kind of fundamental idea in machine learning when it comes to 10 billion buckets, when it comes to such complex data. And with the vision here is if we could make machine learning that could understand language at a less superficial level, truly understand those billions of different ideas and how they go together, then imagine it could kind of go out on our behalf and talk to people and sort of aggregate what ideas are being discussed. And you can imagine a kind of prosthetic where just me, one person, I could have this sort of personal machine learning system, and it could enable me to have one-on-one personalized conversations with maybe thousands of people at the same time, maybe millions of people at the same time. We built all these pipes so we can send messages to each other. We have Facebook and Twitter and all those things, but we can't. We have no attention left. We're down to 5 seconds a message. We can't read it all. So we need an interface between us and that data volume. Yeah. exactly. We could filter out some things too. That would be good. And in the enterprise, because I know a bunch of people raised their hands, those millions of people are customers, and you or me, and we could talk to a company a lot of different ways over a lot of different channels through natural language, and then that company would like to help us and get back to us right away, and there's some people in the company whose job it is to do that, and today they don't really have the ability to do that. We work with one bank that gets 1.2 billion blobs of text per year from their customers. So there's just no way to read all of that and understand what's going on in it. And this problem is getting worse. So over the next 5 years, there'll be an 8x in the amount of natural language data or data in general, and 93% of this data will be open, free-form text and natural language. So this is a big thing. And what ideally we'd like to be able to do is we'd like to be able to take in, so here's a person, maybe their spouse is sick in the hospital, maybe they live in someplace and they're maybe a bit older, they're trying to get into their bank account because they need to maybe pay the health insurance bill, but they can't do that, they need help, but the customer service doesn't get back to them. This is a pretty complex message. This is a paraphrase of a real message from one of our customers. Data. If we could turn this into a structured form, into essentially a database entry, where we could pull out key value pairs or pull out categories, really turn it into something analytically tractable, then we could put it into Tableau, or we could put it into our own gamma and drill down analytics and really understand it. We could put it into a CRM or some kind of database system and go at it. And we could build reply systems that would be able to, tease this apart. Part of this message is saying, hey, we're being a bit rude to our customers. We need better training on this issue. Part of this is saying, hey, we need a better process for dealing with a situation when a spouse is locked out of an account and needs access and needs to get permission to get access to the account. So there's more than one idea in here. They're kind of sophisticated, and we want to pull those apart. And it's hard to do that. So you could hire like a whole bunch of people and try to explain to them, here's the things I want you to look for, the ideas I want you to look for. I want you to go through these billion messages, and I want you to do data entry into a database and pull out the ideas and enter them into this form. And that's really difficult. It's slow, it's expensive. It's about 65% of the time they will get the right entry from what I've seen in data. And it's hard to explain really rich stuff to a large crowd of people who are doing this for you. So you don't get very deep insights, especially if there's something in there you didn't expect. The people from Bangalore or somewhere who are doing this work in the crowd are not going to come and say, oh, actually your batteries have started exploding, or your cars have started accelerating. You've got a problem. You don't hear about that. You could build rules-based systems, but anyone who's ever tried to just take Python or something and apply it to natural language, that's really difficult, right? Like, how would you write code to just have rules? You have some keywords and some stuff like that. It's very brittle. You're going to have to hire coders to do it. That doesn't work. So we're really hoping machine learning is going to solve this problem. But here's what machine learning, as we all know, looks like. So, if you go to one of the big natural language processing houses, anyone who provides AI as a cloud service, for example, and you say, hey, I want to read all my customer messages. Here's what they'll say. They'll say, dump out about 1 million of these, and then we'll send them somewhere, and people will fill in a kind of multiple choice test. And so for every customer message that comes in, somewhere in a foreign country perhaps, will go through and they'll check the boxes to categorize what ideas are present in this text. And each row is a different sort of quiz question. And so we'll send this out, 1 million quiz questions we'll need to aggregate to the answers to train the system. When you get those back, how do you train the system? Well, it's just like training a dog. So you put in the utterance, that's the stimulus or the input. You're doing like Pavlovian conditioning. And then you tell the dog, here's the desired response. I wanted you to check this output box. Bucket it, classify it into this category. And then if the machine learning gets it right, you're like, give it some victual and treat. And if it gets it wrong, you like hit it. Right? That's what backpropagation, gradient descent, stochastic gradient descent does. It adjusts the weights to reduce the errors. So we're Pavlovian conditioning our neural networks and our other kinds of support vector machines and random forests and all the things that we use. And that's sort of okay as far as it goes. I mean, it takes $500,000 in 3 months and 65% accuracy when you do it humans to fill out this exam, this test, and then you train the machine learning. It's no better than the 65%. It doesn't know things that the humans didn't teach it. But what really breaks down is as soon as you get to more columns, right? So if you want to pull out more than 50 ideas or 50 different categories from your text, like 10 billion, then this would be 1 million rows by a 10 billion columns multiple choice exam. You can't do that. There's something wrong here. Language doesn't avail itself of Pavlovian conditioning, right? We're not dogs when we talk, despite the movies. So we've been taking a different approach, and like all good engineering moves forward, you have to actually change more than one thing at once. If you only change one thing, you make an incremental change. We've had to change 4 different things. So first of all, most machine learning models are basically like balls connected by sticks. Whether those are variables in a support vector machine, or choices in a random forest tree, or neurons in a neural network, you basically have variables connected by weights or edges. So we've replaced the synapses in a neural network with arbitrary programs. So so models are now Turing-complete programs. They're actually Python programs. Variables in a normal machine learning system, most of them, unless it's a Bayesian system, it just tells you the answer. It doesn't tell you how sure it is or where the error bars are around that answer. So we believe that you have to put probabilities around every variable. By the way, this is if you want, this could be the last really deep technical slide, and I'll show you just how it works like in a GUI, and we can play demos and stuff. And just for those who like the deeper stuff, and I've got more backup slides. I'm going to skip solvers are locally optimized and globally compatible, although that's an important step. And then really the key thing I'm going to show you today, which is you can't just teach a system complex ideas by giving it stimulus, showing it a response, and training it to give that response. Like if you teach a dog there's food when you ring the bell, you ring the bell, then you give it food, you ring the bell, you give it food, you ring the bell, you give it food. If you teach a kid, like we got a dinner bell at my house, and I have like 2 7-year-olds and an 8-year-old, and you want to teach them that this is the new dinner bell and food is coming, then you say, this is the dinner bell that I just bought, and when I ring it, that means it's dinner time and you should come, and you just say that like once. Or if you're my kids, you say it like 3 or 4 times, but you don't say it 1 million times, right? So what are we doing there? We're taking an idea, and we're doing like Inception. We're sticking it right into the middle of the brain of the child, in between the input and the output. And also we can ask them, what's this bell? And they say, oh, that's the dinner bell. You use that to call us for dinner. So they can tell you what's in their mind, back out. We carry on conversations with each other that go beyond the stimulus response thing. We interact with the middles of each other's minds. And so these kinds of changes, when we started doing this, everyone thought we were crazy. But Jan LeCun, who's one of my childhood heroes at Facebook, one of the pioneers of deep learning, he said, let's leave deep learning. On January 5th, he said, forget deep learning. We need to move to differentiable programming, where models are programs, not neural networks. And some of my colleagues and friends at Google said, this TensorFlow thing needs probabilities in it. And so they started adding that. But we like to think, we started doing this about 5 years ago, so we're actually already pretty good at it. In fact, we've got a product based on it. So let's talk about what we're trying to make here. Let's solve this natural language problem. What would be your ideal natural language system? Like if you all came here to see our talk's called natural language, something, breakthrough, whatever, sorry. What would be a real breakthrough in natural language? What would be your ideal system? Well, you just talk to it, it would learn stuff, right? It would learn how to do things like new Amazon skills or new Siri domains. You just talk to it, explain things to it, and it would learn them. That'd be good, right? No supervised learning at all. It would be super accurate, way more accurate than the natural language systems today, which is like, kind of misunderstand you a lot. And it would just be getting more and more accurate the more it learned. It would be super easy to use. You wouldn't even need to necessarily be a data scientist to teach it things. Maybe you need a data scientist to go edit it and go into its brain and modify it and manage it, but it would be super easy. When it didn't understand you, it would ask you a clarifying question, right? So it would be clear about what it didn't understand, and it would try to learn more. It would be curious, actually. And it would support all languages, because let's make a multinational AI. So I think these are some of the properties, at least, of what the perfect natural language AI system will be. So we made one, so let me show it to you. I'm going to skip over some technical content. Someone will ask me a question and get me back there. All right, so let me show it to you. So here's a system. Over here is where you can say something to it. You type it in. If you wanted to talk to it, you just put a voice-to-text interface in front of it. So here someone said, will someone help me find my points on my statement? So this is a system right now that you're talking to it in order to talk to it about your credit cards and your debit cards and issues you might have. And it has classified it into a category, a subcategory, and then it's maybe pulled out some key value pairs, like other ideas. And this is just one particular idea tree. So we call this the idea tree. It's kind of highfalutin name for it. Basically, this is a breakdown of ideas into a hierarchy that is easy for humans to understand. Now, behind the hood, there's this really complex, deep learning system. Language is this noodle bowl of complicated correlations and slang and acronyms and spellings and ambiguities and syntax and semantics. But we don't want the human, like when I talk to you at a cocktail party, I don't have to break everything I want to talk to you about down into like, this is a noun and this is a, so this is how we talk to our system, is sort of an affordance that we've given ourselves. So it gives us kind of a schematic of how the ideas are organized in the mind of this machine. Okay? And so we can run an utterance into it. So let's just do that. So we train the system, and then we can type something in. Will someone help me find my points on my statement? And it says, okay, that's credit cards, rewards, and a rewards accrual. And if you say something kind of weird to it, like my ATM card, my code is not working for it. So there's grammatical variations, some synonyms. It says, oh, that's a debit card. It's an ATM card. It's a PIN number. It knows that kind of stuff. It knows that an ATM card and a debit card are different because it can read Wikipedia and it can pick this up from various places, from all the data that it's interacted with. I'll show you that. And it says, oh, this person needs a new PIN number because their code isn't working. And it's actually, in terms of doing this, taking in language and breaking it down into a sequence of ideas, it's the most accurate system on the planet. So we've benchmarked it against a number of both highly proprietary systems with clients who are very, very good at doing this kind of stuff, and already with their own data science internal teams. And we've also tried it out against a lot of open source systems. And if you plot the number of training points per class, so the number of labeled utterances that you have to use to teach it, the answer is, how many do you need to use to teach our system? 0. Right? You're already at 0 training points per class. You already have quite a good accuracy. And then as we head to more training points, it picks up and it basically tracks with the very best systems in the world. So it can learn from labeled data, but it doesn't need labeled data in order to learn. If it gets it wrong, however, so say there is an incorrect one, it's not sure about, it'll actually ask you a question. So there is a problem with my card. It's actually 59% sure this is a debit card, because actually 59% of the people who come to this system ask about their debit card. There's about 60-40 debit cards to credit cards in the world. Why did that happen? I think your thing just tuckered out. Yep, well, there it comes back. Let's hope that's not a trend. It said, all things being equal, this is probably a debit card request. And it's clearly something like that. But it's not 95% certain. And we like it to be 95% certain before it goes off and handles your request, because otherwise you're going to be frustrated. So what it'd do in this case, when it notices a threshold below 95% probability,
credit card or debit card?
It asks a question. It said, did you mean credit card or debit card? Well, next time that happens, I'll use my mic. So it asks the question, and this is just a Mad Lib. The black words are just canned, and then it just uses the names of the two nodes, and it just says, you know, this part of the idea tree, this decision, I'm not sure about. Let me just ask you which of these you meant. And if it's clear about everything else below, it won't bother you about that. So for example,
what would you like to order?
Sausage pizza.
Which pizza would you like? If you're not sure, you can also ask for the pizza menu.
Pizza menu.
You can order cheese, pepperoni, or meat lovers pizza. Would you like to hear more?
Yes.
You can order supreme or veggie lovers pizza. What would you like to order?
Sausage pizza.
Which pizza would you like? If you're not sure, you can also ask for the pizza.
That, my friends, is the state of the art. So the bar is a little bit low, but you know, we've all had that experience, right? It didn't understand what we said, it just kept sending us back to the menu. It's just not right. So let's do the same thing with our system. So let's load in a little pizza idea tree. Let's push train. This is a new kind of training data. This tree is a structural hint that tells the deep learning system the organization of ideas that we want it to build in to its system. And so once it's trained off of it, just finished on a laptop, you can say, I want a small plain pizza, please. And now it says, oh great, small cheese pizza. And if you say something to it that's a little confusing, like try this on Alexa.
Pepperoni pizza. No, actually a large cheese.
Play it again.
Large pepperoni pizza. No, actually a large cheese.
So she changed her mind.
Sorry, that pizza is not available. You can ask for the pizza menu.
Okay, so she changed her mind. Let's try changing her mind on our system. Let's type the exact same thing in. Large pepperoni pizza. No, actually, large cheese.
Got it. Large. Would you like cheese?
Right? It knows what it doesn't know. So she confirmed on large twice. It's 98% sure on large, but cheese is only 82% sure. Below the threshold, it has to ask about the choice. So that's all well and good. You can put these ideas in manually, but you know, it seems like, gee, are we going to have to like teach this thing all of the ideas in the world by like hand building these idea trees? That seems bad. So let's not do that. So first of all, you can do that. Actually, I'm going to skip around. So let me just go here. So here's an idea tree we built by hand. And what this idea tree does is it is for booking, changing, and canceling hotel reservations, restaurant reservations, and flight reservations. Okay? It would only take you a couple minutes to build this tree, but let's say we didn't want to do that. So instead what we're going to do is we're just going to take conversations that people have had in the past with our agents or on our chats or wherever. We're just going to load in a whole bunch of unsupervised data. So this says, I need a flight to Denver next week. Can we move my flight tomorrow to the evening? I want to book a table for 2 at Samovar in San Francisco. Dinner tonight was canceled. I won't be needing that room at the Marriott this weekend, and so forth. It's just a big jumble of different ideas about different things. And you can see the system thought about it for a second, and it built the same tree that we built by hand, which is pretty neat. And we can watch it thinking about it. So here it is, considering different scientific hypotheses using Bayes-Occam's razor to find the minimum explanation for this data, and then it produces that tree. So you don't have to build these idea trees by hand. You can build them by a machine, and once the machine builds them, you can send messages through them just like we did before. So if we say, book me a flight to Denver, then it will categorize that message. Not just categorize at a top level. Categorization would just be obviously the top branch, but then it's also giving the subcategory and pulling out other things. Here it's decided to put brands a level down So there's different brands of hotels. It might be a brand hotel, or you might just say, book me a hotel, and not specify the brand. So it has created some different branches for that. Now you can interact with the system. So if you do want to have auditability and control, then what you can do is, for example, if a system, if someone says something to your system that comes in, and it's not, you didn't build any branch for it, it's not used to seeing it. Please play. Okay, that video didn't play. Let's try this one. Yeah, here's a video there. Sorry, let's fix this. Has anyone ever edited a video in front of you on a talk? Yeah, that's the problem. All right, here we go. All right, so here's something that no one's ever said to the system before, and the human who built this tree didn't think of it. I think my account was hacked. It goes into the unknown category. So you come in the morning, customers have been talking to you for 24 hours, there's a bunch of stuff in your unknown bucket. And you say, okay, well let me build out some tree for that. So what I can do is I can put in an account issue, and I can put under that some different kinds of account issues like identity theft or logins, that kind of thing. And I can just go ahead and build that out. And now if that same utterance comes in, I think my account was hacked, then it's happy and it'll correctly classify it. So it can build trees, you can build trees, and you can collaborate it with it. So say one person builds one part of the tree, and one person builds another part of the tree, or the machine learning builds one part of the tree, then you can put them together, and it'll just work all together. And so what that opens up is a possibility for a kind of collaboration between people and machines to create systems of ideas, and even to share ideas between each other. So we can make a marketplace, which are really just subtrees, where we could share them between our AIs, between each other. And so if my AI is more polite than yours, I could give you my politeness module. And if your AI understands account hacking better, you could sell me your account hacking module. That's really neat. We've never had the ability to pull apart a machine learning model and sell or exchange parts of them to each other in order to increase knowledge. We all do that with each other. We sell magazines and books and blog posts. This is a new way of trading information that isn't written information. It is written information made into a mechanical system that embodies those ideas. So let's see, choose your own adventure. It's 3:30. Would you like to see some applications of this kind of thing right away, or would you like to see a little more about what's under the hood? Raise your hand for under the hood. Under the hood, okay. Let's do it. Then we'll come back to applications at the end. How about that for a deal? All right, so I'll take that call for under the hood as incredulous amazement at the coolness of the thing we've built. All right, so here's what's under the hood. So the first concept you need is how to write what we call a probabilistic program. And then what you need is the concept of how to have a machine write a probabilistic program. So I'm going to do this for a simple example that's easier to understand than natural language. I'm going to do this for recognizing basic shapes. Okay? So in fact, we made a little demo of this. So here's a little app we made where you can draw shapes, and then it recognizes what you drew, and it replaces it with a better version of what you drew, right? Which is nice if you're bad at drawing like me, and you're wiggly and wobbly. It's really pretty fun. In fact, in some ways, we were playing with this, and then I went and actually tried all the other, we just made it one afternoon in the lab, all the other sort of Microsoft Surface and Adobe and all the other kind of thing. And they all just sort of, you draw a triangle, they'll recognize you drew a triangle and replace it with an isosceles triangle of unit shape in this orientation, kind of roughly in where you drew the triangle. That's kind of the state of the art. But this thing, it really replaces it with the thing that you meant to draw. Deeply, 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 you're yeah, that's what I meant to draw. And that's really, I think, the promise here, is that machine learning could know what we meant to do, what we wanted, and give it to us, instead of what we did do. But in order to do that, we have to be able to put ideas into it, because it needs to have the concept of what would be our platonic triangle, not just like learn from all my wiggly triangles. Then it's just going to learn about wiggly triangles, which is not what we wanted. So how do we do that? So what we're going to do is we're going to write a program, first of all, that makes triangles. So do you guys know how like cell phones work? So cell phones transmit radio signals, and they take your voice, turn them into bits, and then they send them, right? But what they do with those bits in the transmitter is they do a bunch of things. They add parity bits for error correction, and they modulate them, and they do all these steps. And the people who decide those steps are the IEEE standards bodies, right? And then when your cell phone receiver, whether it's the base station or whatever, receives the cruddy wireless signals that actually come across the urban canyon and give noise and everything, your receiver knows what the IEEE decided for the transmitter, and then it solves an inverse problem. It's like Plato's cave. You see just the cruddy image, and you have to guess what's outside the cave, the real 3D beautiful thing. You have to guess back to what caused the data. Right? Data science, actually science, is the process of coming up with an explanation for where data came from. So what this is where triangles come from. So first we choose a corner of a triangle. Triangles have 3 corners, right? Last time I checked. Then we're going to pick another corner at random. Triangles could have their corners in different places. We don't know where every triangle's corners are going to be, so we'll choose those at random. But then we're going to say, look, draw a straight line between those 2 points. So this is a cooking recipe for cooking triangles. It's just like following a recipe in a recipe book. It's just a simple Python program. Then we're going to start at that endpoint. We're going to choose a third corner at random, draw a line, and we're already doing something that a neural network or a random forest can't do. Because what a neural network would do is it would say there's all these points, and I'm going to try to learn what a straight line is. Here, we get to tell it what a straight line is. We just say, like, it's the locus of points that's in a straight line between, like we can render from any line drawing program. When we take that last corner, there's no more randomness left, and we're going to connect the dots. So there are 3 random choices in this program, plus some determinism. The things that we knew we wanted, like straight lines, we told it, and the things that we didn't know what we wanted, like the corners and where they are, we let it guess. A probabilistic program can combine guesses and determinism in any combination you want in order to make a theory of any piece of data and where it came from. So you just write a cookbook recipe that makes your data like your data. So like I draw really wiggly, bad green triangles. The system cooks its own red triangle. They're not exactly the same. What I can do is rerun the program, but choose different blue choices and see if I can move those blue choices a little closer to the data. I can do that over and over again until the output from this program fits the data. Now that sounds like a terribly expensive thing to do. It is. What you have to do is run the program over and over again at random. For example, I don't have a video of that for a triangle, but I have something better. My friend Dan Paluska, who's the drummer in my band at MIT, became an organic hippie farmer off the grid, so I had to make a fun of him by making an art project. So this is, instead of a triangle with 3 corners, this is 300 corners. And instead of straight lines, what this says is there's this one single point curve that has to go through all 300 points. It's 50% transparent. And if you just keep moving the corners around, eventually, and comparing it against Dan, my picture of Dan, eventually this one single Bezier curve looks like Dan. So we just did curve fitting. Well, like a pretty cool kind of curve fitting. We said it had to be one curve and it has to fit this data, in this case an image. And so we don't actually just pick up corners at random and move them. The whole magic here is how you actually solve backward through the program. But that's several PhD theses, and that would take us longer than we have today. But once you have that, then you have a probabilistic program. You can compare it to what you draw. It'll do a bunch of iterations behind the scene on this iPad in real time, fit to the things you draw, and then replace what you drew with what it fit to what you drew. That's what's actually happening in here. The only problem is, And by the way, the triangle that it's recognizing there is running the triangle program we just wrote. No different. You can see it in Python, it has some Pythonese, slight, but it's basically English. I mean, it's basically just wrote a story for triangles. Still, we don't always want to have to write all, you wouldn't want to have to sit down and write the rectangle program, the octagon program, and all like this. So let's get it to write the triangle program. All right, so what's the best deep learning you can do for that? Well, Google Quickdraw is an app that is deep learning based that a team at Google put out. They asked people to come play Dictionary. They say, draw a floor lamp in 20 seconds. We drew a chair next to a floor lamp because we like to read in a cozy chair. It said, is this a church, a house, a jacket? I'm not sure. Why the heck didn't you make a floor lamp like all these other people? When I asked them to draw floor lamps, here's what they gave me. And my answer would be, we did. Our floor lamp looks just like those people's floor lamps. Right? There's our floor lamp. It's pretty good. Maybe it had some light rays around it, but it looked like a lot of the other floor lamps that people drew. So why didn't it get it? So what we're going to do instead is we're going to start with an even simpler program than we wrote. This is not even a triangle program. This is just a line program. It picks 2 points at random and draws a red line between them. That's it. So all it's going to start with is a basic concept. Everything else it's going to figure out on its own. So first let's test it. Does it recognize lines? Yes. If we draw lines, it will use its line program and fit the lines. Good. Okay. 4 lines. Let's tell it the name for this new object. We'll call it a rectangle. And then we said, write your own program that, and what it did just in the instant was, we've sped up by 2x. I need to slow it down again. We should do that. What it did in that instance is it wrote a program just like the triangle program that we wrote, but it had 4 corners instead of 3. And 4 lines instead of 3. But if you went and read the Python that it wrote, it looks just like the program we wrote. And then once it writes that program, we can draw a bunch of rectangles, and it'll recognize all of them as a single blue object. But it remembers what lines are, because it knows it made its program out of 4 lines. Those are subroutines. And so it says line, 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 line makes a rectangle. So it actually, like, I don't know if you've played with image analysis in Tensorflow or something, but if it recognizes a cat and you say, well, what's that? It's not going to say a whisker or an ear or a paw or the toenail on a paw or the bacteria on the toenail and the paw, like down in the valio. Like, it's not going to, it can't do that. It doesn't know what things are made of. It doesn't have an object, ideas. The system does. We can just keep building more things. So we can teach it. Here, unfortunately, we named it lamppost. We should have just called it post. We should fix that too. And then we can use that post and the rectangles we already taught it, and we can say, here's 2 examples of a new object. We're going to call it a lamp. Lamp. Write a program that explains both of those lamps. And so it says, okay, lamps have 2 rectangles and a post. And the post seems to be different heights. You can have a desk lamp, a floor lamp. So now let's recognize some objects. We draw some other lamps, different heights, ask it what it sees. It says these are all lamps. They're made of posts and rectangles, and those rectangles are made of lines. If we draw something that didn't really vary the way the examples did, like here's a kind of a tomahawk and a cat scratching post and a flagpole, it says those aren't lamps. I see rectangles, I see posts, but those aren't lamps. Because they didn't vary in the way that we showed it.
So is it building its ability to learn based off the labels that the user inputs?
No, those labels are just there for us. So when it labels stuff, we can read them. The labeling had nothing to do with the learning. Yeah, so it looks at the kinds of variations that there are, and it has choices for different kinds of angles that could show up, and it says, well, there's a lot of angles in here, and they all seem to be kind of around this 90-degree setting. So it's learning that trend. And there's this thing called Bayes-Occam's razor, which is well, Occam's razor is the simplest explanation is the right one. Bayes-Occam's razor kind of extends that to probability theory. You can go read about it on Josh Tenenbaum's website at MIT. But that has a lot to do with why this works. Because it says, yes, there are a billion different possible angles out there, but gee, all these ones seem to be like really tightly clustered around 90 degrees. Let's assume there's something special about that. So we can just keep combining ideas and combining it into more and more complex topics. And so here's a lamp and a chair, and no matter what orientation we draw them in, what sizes, and we could teach it a different kind of chair, and we could also draw a lamp with all kinds of other stuff around it. No problem. So what we just saw was one person teaching it. Google's Quickdraw with a deep learning system, pretty good group. They collected 8 million message drawings, sketches from over 100,000 people over a period of 4 months. The examples I just showed you were the examples it used. It was running on that iPad. Google reportedly used 100 GPUs for like a month to train their system. And it was running in 2x. I just sped up the videos by 2x, which we need to slow down to 1x because it would be more impressive to just watch it. It works in real time, essentially, on an iPad. So that's a little bit more about what's under the hood here. And so, when I say we replace neurons with programs, think of the corners and the triangles as the neurons. Like those are the things that can change their activations. Those are the things that you're trying to guess what should their value be. But the lines, the sort of connections between the corners, we've generalized that to not just be always a sigmoid function and addition, not just like what a neural network has, generalize that to be any program, in this case render a line deterministically. So the programs, and then we put uncertainty because we need probabilities in order to really make the system compositional. If every corner knew exactly what it thought all the time, they'd just fight and you'd never be able, they need to be able to sort of anneal to fit your data. And that's why they need to have, when they're randomly wandering around, they need to kind of have error bars around the solution. And then it can kind of settle down. But it shouldn't be overly certain about what it's seeing, because then you can't put subroutines in, you can't build it modularly, you can't stack it up. Yeah. The question is, could you do real images with this? We haven't done it, but if you'd like to do it as a project, here's how you would do it. You would take a 4x4 pixel sift feature, and you would say that, and you would make, a little library of those, standard, like the bottom layer of a pre-trained neural network. And then you would, instead of a line program, you would give it a choice over those sift features as the fundamental elementary object, and then you'd let it just build up cats out of that. Yeah, so this is not back to any world. This is forward to a world that combines all the other worlds. So, do I have the slide? I'm sure I do. No. Somewhere here, I have an LSTM, deep learning LSTM, written in particle. I don't know if I'm going to be able to put my hand, there it is. Okay. So here's the first part of an LSTM written as a probabilistic program. What is the assumption that a neural network makes about the transmitter? The transmitter, first of all, a neural network, you usually think of like you put the image into the input, and then you get like this is a cat, like the classification out of the output of the neural network. All right, screw that. I told you we model transmitters in science, we don't make receivers. So what is the theory? The theory is someone decided among horses, cats, and dogs to show you a cat. And then they grabbed an image for a cat and they generated that image and then they sent you the image. And what you get the image, what you're trying to do is invert that theory and go back to what did they mean to tell me? They meant to tell me they're thinking of a cat. Okay? That is the right way, going back to Claude Shannon, to think about communications, information theory, and machine learning. So don't do anything else. All of science works by making theories of where data came from, transmitters. So the neural network here starts with the output, what we call the output. It starts with flip bits, which are the output neuron layer of my LSTM, to turn on what category I'm going to show the person. And just like a generative antagonistic network, just like the generative part, I'm going to filter down through a bunch of weights in that LSTM and through all the neural connections until I generate what is usually thought of as the input of the neural network, until I generate the image or the sentence. Okay? That's the theory of that. That is the scientific theory. Now, if you haven't trained the neural network, if your theory is like, here's the category and here's the image, and the neural network has a billion random weights in it, which this one does, then what you're saying is I know nothing about my transmitter. Which is fine. Maybe you don't. Maybe you don't have any theory or any idea about where your data came from. So a good example of that would be, I know nothing about the stock market. If you asked me to predict the stock market, I would do the following thing. I would take a ticker tape. I would start at 2009 because I would assume that pre-2008, structurally the stock market, the economy was like some different set of statistics. But I'd start at 2009, I'd get the ticker tape, I'd take 10 ticks of a company's stock price, I'd put that as the input to the neural network. I would take the 11th, I'd put that as the output, I would train the neural network on that input-output pair, I'd move over by one, I'd train it again, I'd make a batch of learning system. Because I don't know anything about the stock market, I don't know how it works, I don't pick stocks, I don't know about companies. So fine, a universal function approximator with a bunch of weights, regression, multi-layer regression, which is what this neural network is, all neural networks are, would be a fine theory for me, and I would just need a lot of training data to fit the weights to invert the model, to train the model and then be able to invert it. But that is almost never the case. Almost all of us, if we're hired to predict something, know something about it. And so what we're really doing here is just saying, well, when we know something, like triangles have straight lines, let's tell the system. Not yet, not yet. That's going to be interesting. Yeah, haven't done that yet. What we have done, however, is we've taken idea trees in English and just translated them to Spanish by, instead of translating the training data, translating the model. And guess what? The accuracy was almost identical. It worked really well. We're able to take the middle of the model, just translate the words in the model to a different language, and that works pretty well. What we missed was, in Spanish, there was like Jose Maria or something. Like a lot of people had two names, whereas like in English, a lot of people had like, it was like Bill, like it's one name. And so we had, like there were some things where we had to augment the model because like it was expecting names to be like one word. But other than cultural ideas like that, which, if I went to visit a Spanish-speaking country, I would have to and I'd never seen Spanish, I'd have to also learn that, right? So why is everyone always, So the translation mechanism felt very similar to like what it would be like for a human to translate. What we didn't do was like go get a whole bunch more messages and categorizations in Spanish and train a new neural network. Yeah, so we figure each customer might have some domain-specific things that they want their bot to talk about with customers. So that part they can train. And if we work for two car companies and they both laboriously built the same subtree, we won't take that subtree and give it to any other customer, and we won't share it between those two car companies because we figure that's unique to car companies. Yeah, concepts, yeah. We're 6 minutes over, so you'd be excused. Why don't we say we're done, since no one's going to come and save us. And if you'd like to ask more questions, come on up. All right,